In the everyday world, it's easy to see entropy at work. Ice melts into water, a neat arrangement of items becomes scattered, and once you shatter a vase, it never magically reassembles. This is the second law of thermodynamics in action: disorder increases over time. However, quantum physics appears to present a contradiction. Mathematical calculations often show that entropy in a quantum system doesn't seem to change. Welcome, everyone. Today we're diving into one of physics' most fascinating riddles: entropy in quantum systems. You may have heard that, according to the laws of thermodynamics, entropy, or disorder, must always increase in a closed system. But in quantum physics, that idea seems to hit a paradox. Let's explore why and how scientists at TU Wien have found a way to resolve it. Could it be that in the quantum realm, the rules of thermodynamics are being broken? A research team at TU Wien studied this issue and made a crucial discovery: the definition of entropy you use matters. Traditionally, physicists have relied on something called von Neumann entropy, which, for a perfectly known quantum state, remains constant. That seems to say disorder doesn't grow. But if we measure entropy in a different way, specifically using something called Shannon entropy, we find that disorder does keep increasing, just like in classical physics. Let's break that down. Imagine you have a box of perfectly sorted colored balls. That's a low entropy situation, very ordered or very specific. If you shake the box, the balls mix, and you get a disordered look. Now it's high entropy. Why? Because there are countless ways for the balls to be mixed up, but only a few ways for them to remain in that neat, original order. Classical thermodynamics tells us the system evolves to higher entropy over time. Physicists often say entropy gives us the direction of time. When you go forward in time, entropy increases. When you go backward, entropy would decrease, something we just don't see in nature. But quantum physics raised a puzzling question. The so-called von Neumann entropy of a pure quantum state doesn't change at all. So how do we reconcile this with the second law of thermodynamics? Here's the key. Von Neumann entropy assumes you have full knowledge of the quantum state, every single detail. But quantum theory itself prevents us from knowing everything about a system. When we measure a quantum system, we choose one property to observe, like position or speed, and quantum mechanics only gives us probabilities for each outcome. There's always an element of surprise in the measurement result. And that is where Shannon entropy comes in. Shannon entropy measures uncertainty based on probabilities. If one outcome is guaranteed with 100% certainty, Shannon entropy is 0, there's no surprise. But if there are many possible outcomes, each with similar probability, Shannon entropy is high, lots of uncertainty, a lot of potential surprise. When you start with a low entropy state, where maybe one outcome is far more likely, and let time evolve in a closed quantum system, those probabilities tend to spread out. Over time, you get greater uncertainty about what measurement result you'll see. That is the growth of entropy in quantum mechanics. So, the TU Wien team ran simulations to confirm this. They looked at how these probabilities evolve in closed quantum systems with multiple interacting particles. As it turns out, the Shannon entropy rises from a low value and eventually levels off, just like in the familiar thermodynamic picture. That means quantum systems do move toward more disordered states, even without any external environment. This discovery isn't just academic. We're on the cusp of a new era in quantum technologies: quantum computing, quantum sensors, and more. Handling many-particle quantum systems requires us to blend quantum theory with thermodynamic principles. By clarifying how entropy actually behaves, researchers believe they can better design and control complex quantum processes. That could mean more robust quantum computers and innovative quantum devices on the horizon. In summary, the second law of thermodynamics is alive and well in quantum physics. You just have to use the right definition of entropy. When Shannon entropy is considered, it becomes clear that even in a perfectly isolated quantum system, disorder increases over time. This new understanding bridges the gap between classical thermodynamics and the weird, wonderful realm of quantum mechanics. And who knows what future breakthroughs it will inspire. Thank you for joining us on this journey into quantum entropy. If you enjoyed learning how TU Wien researchers solved the paradox of disorder in quantum systems, be sure to like, share, and subscribe. We'll be back soon with more mind-blowing science. Until next time, stay curious.